discuss about the closed baked structure. Now in this case we discuss what is the meaning of closed baking. Means the constituent particles are arranged leaving the minimum vacant space. This is referred as a closed baked structure. We'll discuss this baking in the 1 dimension, 2 dimension and 3 dimension. First of all, see closed baking in 1 dimension. Now in this case, the arrangement of particles in a row and touching each other. We are assuming that particles are sphere in size, and if they are in a one row and touch to each other, then this is called closed baking in 1 dimension. Now we can say in this case each particle, like this is the particle, and this is in close relationship with this and this. So these are the nearest neighbors, and this nearest neighbor is known as the coordination number. Number of nearest neighbors of a particle is called its coordination number. So we can say in this 1 dimension the coordination number is 2. Now we will discuss next in the closed baking in 2 dimension. Now see, we will discuss if closed baking in 1 dimension is arranged like in this way. This is one row, then this is second row, this is third row, and this is fourth row, and so on. So we can say in this case the spheres of the two rows are aligned horizontally as well as vertically. So we can say there is a alignment horizontally. Now what the meaning of this horizontally? This is your horizontally alignment and this is vertically alignment. And if first row is known as the A type row, as mentioned here, this is A type, so we can say the arrangement in all the row is same as in row A. So this is known as A type arrangement. Now in this, if we say that is each sphere, so this is the sphere and this nearest neighbor of this sphere is 4. This is 1, this is 2, this is 3, and this is 4. If we join the center of these spheres, then we will get the position of square clothes. We will get the square shape. That's why this is known as the square clothes baking. And in this center atom is attached with the 4 another atoms. That's why its coordination number is 4. Now next, if second row particles of the second row, they fit in the depression of the first row. Now what the meaning of this depression? You can say this is your first row and this place, this is called depression. This is the depression. And this is the particle of your second row. This is second row particle, this is second row, this is second row, this is second row. So we can say the arrangement in the row A is different. Arrangement of atoms in the row B is different. If we repeat the third layer, that is third row, then this first and third row align together. Atoms in the first and third row align together. But arrangement in the alternate air is different. That's why this type of arrangement is known as AB type arrangement. And this is more closed baked structure because in this case the vacant space is less compared to this square closed baking. Now in this case we can say this is your, if we select the one atom, this atom is surrounded by the 6 nearest atom. This is 1, this is 2, this is 3, this is 4, this one is 5, and this one is 6. If we join the center of these atoms, you will get the hexagonal closed baking, and that's why its coordination number is 6, because this is surrounded by the 6 another atoms. This is coordination number 6. So we can say this one is known as the square closed baking in 2 dimension, and this is called hexagonal closed baking in 2 dimension. Now we'll go to the baking in 3 dimension. Before it, if we again see the hexagonal closed baking in the 2 dimension, now just see, this is the one vacant space. This is the vacant space. This is known as void. We use the word void, and this vacant space touch 3 spheres. This is 1, this is 2, and this one is 3 sphere. And if we join the center of these spheres, then we will get the one triangle. Get the triangle. And this void is situated at the center of triangle. That's why this is known as triangular void. This is called triangular voids. So you can say the vacant space between three touching spheres whose centers lie at the corners of an equilateral triangle. These vacant spaces are called the triangular voids. Now these triangular voids are two types. Now see, in the one row, the apex of the triangles are pointing upwards. Now if you say like any two row, if you say like in this case, this is apex and this is upward. And if we say this is the apex of the second row and this is downward. That's why we can say two types triangles are there, in which the apex pointing upward, and in this case the apex is pointing downward. So two type of triangle void is there. Now closed packing in 3 dimension. Now we'll discuss first of all 3-dimensional closed packing from 2-dimensional square closed peg structure. So if we take like this, if second layer, now if we say this is first layer, you can say this is the first layer which is closed pegged in the 2 dimension, and which is a square closed pegging in 2 dimension. Now if particles of the second layer are placed like this, that is particles of the second layer is just above the first one, particles of the third layer is again just above the particles of second layer, and so on. So we can say that is in this arrangement, spheres of both the layers or all the layers are perfectly aligned horizontally as well as vertically. And the arrangement is same in all the rows, all the layers. That's why this is known as AA type pattern. AA type pattern. And generally this lattice generated is the simple cubic lattice. Simple cubic lattice, and its unit cell is the primitive cubic unit cell. So this is called closed pegging in 3 dimension from the 2-dimensional closed pegged structure. Now if we see 3-dimensional closed pegging from the 2-dimensional hexagonal closed peg structure. Now if you will take the hexagonal of the 2 dimension, and then if we take the one layer, now just see, this is the one layer I am highlighting from this. You can say this one is the dark red color circles. This is your, is it clear? This is the 2-dimensional hexagonal closed pegging layer structure. Is it clear? In the same way, this one is, this is also there, and this is. Now if we want to place the second layer particles, so now just see how can we place these second layer particles. If I take this color, so this is your second layer particle. Clear? This is second layer particle, and this is just above the triangular void in the first layer. Triangular void in the first layer. This one is your second layer particle. Clear? This one. So in this way you can see this one is there, and this is your second layer particle. This is another your second layer particle. So now in this way you can see that is second layer particles are just above the triangular voids in the first layer. Now in this way you can say half of the triangular voids of first layer is covered by the particles in second layer. Now just see this is the this one which we are indicating by another color, this is a triangular void, this is triangular void, this is triangular void in the first layer, this is the triangular void in the first layer. So this triangular void is covered by the particle in the second layer. In the same way, this triangular void is also covered by the particle in second layer. But just you see, this is the triangular void which is not covered by the particles in second layer. Clear? Now in this way, again we are having the some new type of voids. Now just we will see these, what are these types. So this is the arrangement of the two-dimensional hexagonal layer in the first layer and in the second layer. So again we can say second layer of particles are just above the triangular voids of the first layer, and half of the triangular voids are covered by the particles of second layer, and we will get the some new voids. Now see what are these voids. This is the tetrahedral void. Now again we say, you can say this is the particle, this in the blue circle, this is blue, this is the particle in first layer, and when we place the particle in the second layer, this cover this triangular void. So now we can say this void is touched by the force pairs. This void is touched. Now this void is touched by the force pair. That's why, or we can say this is the center at the tetrahedra. Center at the tetrahedra. If we join the center of all these force pairs, this is void will get. So this is called tetrahedral hole or tetrahedral void. Now in this case, another type, octahedral void. Now just see this blue color, this is the particle in first layer, this is particle in first layer, that is A layer we indicated. Now this is the red circle, these are the particles in the second layer. This is second layer, this is second layer, and this is second layer. Now in this way we can say this hole, this is the combination of two triangular voids. One triangular void in A layer or in the first layer, and another triangular void in the B layer. So we can say this is touched by these six spheres. This is the six spheres. If we join the center of these six spheres, then we will get the octahedral structure. That's why this is known as octahedral void. We will get this one, octahedral void. So how can we define the tetrahedral void? So simply we can say this is the tetrahedral void. This is in between the four spheres, but these four spheres should be in the two layers. And in case of octahedral voids, this is the combination of two triangular voids of adjoining layers. So two triangular voids. This is tetrahedral void and octahedral voids. So these different type of voids are there. Now again remember, we will also discuss this thing. If there are the n spheres in a closed packed structure, then there will be the n octahedral voids and 2n tetrahedral voids. This will come detail in the next slide. Now see, now if we place the third layer over the second layer, then we will get the two type of structures. Now see, in the first structure, this one is, we will place these particles of the B over the triangular voids of the particles in the layer A. Now if particles of the third layers are just aligned as the particles of first layer, that is A, first layer is A and third layer is A is the same, then we will get the one structure, or we will get the pattern of AB type pattern. Like see, this is A, this is B. Now pattern in this third layer is also similar to the A1. Pattern in the fourth layer is similar to the B. That is, arrangement in the alternate layer is same. So this is called AB pattern, and in this way we will get the one shape or structure or geometry that is known as hexagonal. That's why this is known as hexagonal closed packing. Hexagonal closed packing. HCP stands for hexagonal closed packing. So now again see, if particles in the third layer like this. Particles in the third layer are just above the octahedral voids. Just remember, particles in the third layer are just above the octahedral voids. Then we can say arrangement in the C layer is different. So we can say that's why this is called ABC type pattern, and we will get this type of geometry, and this is called cubic close paking, CCP, cubic close paking, which is similar to the FCC which we already discussed, that is face centered cubic. So we can say in three-dimensional close paking we are having the two type. One is hexagonal close paking, another one is the cubic close paking, which is arises from the hexagonal close paking in two dimension. Is it clear? Now in both the cases, like this is HCP or CCP, which is similar to, both are similar to the FCC. They are highly efficient, and this the 74% in the crystal is filled. This calculation we will do later on, how the 74% will come. And in both the cases, the coordination number is 12. That is in HCP and CCP coordination number is 12. Then how can you justify this coordination number is 12? Now just see, if we consider this is the particle, this is the particle in HCP. This particle is surrounded by this the particle, and this particle is surrounded by the these six particle in same layer, in the same layer, and three particles are above the layer and three particles are below the layer. So that's why we can say this particle is surrounded by the 12 atoms. That's why its coordination number is 12. In the same way, in this case you can also find out, if we consider this one, like say this one, in this case this is this particle, this is the particle, it is surrounded by the six atoms in the same layer, three atoms below the layer, and three atoms, if we assume that B layer is above that is, so three atoms above the layer. So that's why this particle is again surrounded by the 12. That's why its coordination number is 12. Hope this concept is clear to you. That is how this HCP and CCP structure arises from the close paking in two dimension. Clear? Now next one is, you can also see this, if third layer particles are over the octahedral void, this is octahedral void, third layer particle, that is C1 is different, then we will get the ABC type arrangement, and this cubic close paking CCP, this is the similar cubic close paking. But if we see this, if tetrahedral voids are covered by the third layer particle, tetrahedral voids are covered, then we will get this one AB type arrangement. Okay, so this is CCP and HCP type arrangement. Now what is the position of these tetrahedral voids and octahedral voids in the CCP or FCC structures? Now just see, if we consider this is the FCC, this is FCC. FCC means at the corner, this one is corner, all the corners are occupied. This is 1 2 3, this is 4, this is 5, this is 6, this is 7, and this one is 8, and this one is face center. This is one face center, this is another face center, 1 2, clear. Then this is 3, then face center is 3, this is 4, this is 5, and this one is in front, this is 6. These are the face centers, 1 2 3 4 5 and 6. That's why this is FCC. Now this big cube can be considered as the combination of 8 small cubes, which already discussed, 8 small cubes, and in 8 small cubes there are the, you can say this one small cube, if we consider like this is which small cube, you can see that is if we consider this small cube, this one, this just a minute. This is the small cube. Clear? Like the 8 cubes are there. Now in this case, the particles are present at the opposite side corners. Like see, this is the one particle, this is another particle, this is the phase diagonal. This is phase diagonal. This is your phase, and this particle at one corner, and this is the particle of another corner of the phase. In the same way, this is the phase diagonal. This is phase diagonal. If we join these four, then we'll get the tetrahedral structure. And in the tetrahedral structure, this is the in that is middle or in the center of this tetrahedral, this is a vacant space. So we can say there is a one tetrahedral void in each small cube. Tetrahedral void in each small cube, and there are 8 small cubes. So we can say there are 8 tetrahedral voids in total. Now just see, each small cube has 4 atoms, and when joined to each other they make a regular tetrahedra. Thus there is a one tetrahedral void in each small cube and total 8 tetrahedral voids in a cube. Now we know. Now if we say these, what is the location? So we can say this is at this center of this tetrahedra. Now we can say this, we can assume the tetrahedral voids are located at the body diagonal. Body diagonal. Now what the meaning of this body diagonal? Now if we say, if we join this opposite corner of a cube, opposite corner of a cube, so this is if joined with the, we can say this one. So this is called body diagonal. This is a body diagonal. In this we can say that the 4 body diagonal is there. Now this is one. If we say this is joined with this, if we join this with this is the second body diagonal, and then this may be joined with this. This may be joined with this. Its opposite is this one. This may be joined with this. This is the third body diagonal, and this is joined with this one. This is the fourth body diagonal. And on each body diagonal there are the 2 tetrahedral voids. Clear? There are the 4 body diagonal and there are 2 tetrahedral voids. So we can say how many total tetrahedral voids are there? There are the 8 tetrahedral voids are there. Clear? Now we already discussed that in case of CCP structure there are the 4 atoms per unit cell. So when atoms are 4, then what were the number of tetrahedral voids? And number of tetrahedral voids are twice of this, that is 8. We already discussed it. If number of particles in a CCP structure is n, then number of tetrahedral void is 2n. So this is the location of tetrahedral void and number of tetrahedral voids. Now that's why total number of tetrahedral voids are 8. Now see, octahedral void. How can we locate the octahedral voids? Now just see. Again, if we consider thus FCC or CCP, then the body center of the cube, remember, body center of the cube is not occupied. There are no atom at the center of body. So we can say, and this is surrounded by the 6 atom on face center. Now just see, if we consider the center of this body, this is the center of this body, and then this center of this body is nearest neighbor. Nearest neighbor of the center of body is the particle situated at the center of face. Like this is 1, this is 2, this is 3, this is 4, this one is 5, and this one is 6. And at the center of this there is a one void. So that's why. And if you join these center of these atoms situated at the center of face, then we will get the octahedral position, octahedral shape. That's why one octahedral void is situated at the center of body. You can say the unit cell has one octahedral void at the body center of the cube. Now beside this, we can also locate the another octahedral voids. There is one octahedral void at the center of each of the 12 edges. Each of the 12 edges. I already discussed in one cube there the 12 edges are there. And on each edge center, on each edge center there is one octahedral void. How can is? Now again this is surrounded by the 6 atoms. Now out of this is 4 belong to the same unit cell. Now just see, this is the unit cell is represented. So this is 1, this is 2, then this is 1, 2, and this is 3, this is 3, and this one is 4. This one is 4. 2 on the corners, 2 on the corners, like this is the one corner and this is the another corner, and 2 on face center, 2 on face center. So this is one, this is the one face center and this is the another face center. 2 and 2 belong to the adjacent unit cell. This is belong to the adjacent unit cell. So we can say there is one octahedral void on one edge center, and as we know there are the 12 edges. There are 12 edges. So we can say, and each edge is shared by the another 4 cubes. Each edge is common among the 4 cubes. That's why there are the 12 edges, and it's only 1/4 part belongs to the 1 cube. That's why number of octahedral voids which are situated at the edge center is 3, and 1 octahedral voids at the body center. That's why total octahedral voids are 4. Is it clear? Now again we already discussed, if n is the number of particles, then n will be the number of octahedral voids and 2n will be the number of tetrahedral voids. Now sum up whatever we have discussed. This one is, if n sphere in a closed sphere, then we are having the n octahedral voids and 2n tetrahedral voids. So if in FCC or CPP atoms A occupy all octahedral voids, remember it, A atoms are present at the octahedral voids and B occupy the lattice points, normal lattice point, that is it may be corner along with the center of the body or along with the face center, but in case of FCC the particles are present at the corner as well as center of each face. So what is the formula of the compound? So we can say there is A particles are present at the octahedral voids, clear, and as we know in one there the 4 octahedral voids are there. So that's why number of A atom is 4 and B occupy the lattice point. So in case of FCC, 8 corners and 6 center of the face are occupied and their contribution is 4. Their contribution is 4, and this actually, this is by mistake, it should be B. It should be B. Clear? Remember it should be B. So we can say there is 4:4 ratio between A and B. That's why their formula becomes AB. Clear? In the same way, if A occupy the tetrahedral voids and B occupy the lattice points. So as we know, tetrahedral voids are 8. That's why number of atoms of A particle is 8 and B are present at the lattice points. So their contribution is 4. So that's ratio of the 8:4 is 2. That's why formula is A to B. I think it is clear to you, and that's all. Next time we'll discuss what is the packing efficiency. Actually there are some problem is also there, I think. Yes, some numerical problem is also there, and I am also giving the answer, just you find out how these answers came. A compound is formed by the 2 element X and Y. Atoms of the element Y, it is anion, make CCP, clear, which is similar to the FCC, and those of the element X as cations occupy all the octahedral voids. What is the formula of the compound? Answer is XY, but how this XY will come? So as we know, when we write the formula, already discussed, cation is written first and anion is written later. So in the X is cation and X occupy all the octahedral void. That is, you can say this is X is octahedral void, that is octahedral void. How many octahedral voids are there? 4. Octahedral voids are 4. And anions make the CCP arrangement, that is, this is Y, this is CCP arrangement, that is number of particles are again 4. So ratio of 4:4 is 1, that's why formula becomes XY. Is it clear? Now come to the next. Atoms of element B form HCP lattice and those of the element A occupy 2/3 of tetrahedral voids. Now again in this case cation and anion is not mentioned, but in this case when we write the formula we have to follow the alphabetical order. But if cation and anion is written, then write the first formula of cation followed by the anion. Now in this case where A is present, we can say B form HCP lattice. B form HCP lattice. तो आप कह सकते हैं this is B. HCP lattice means its number of particles, you can assume that is this is N. This is N. And A occupy, and this one is 2/3 of tetrahedral voids. So when number of particles are N, then number of tetrahedral voids are 2N. And 2/3 of 2N. तो आप कह सकते हैं this is multiplied by, this is 2 by 3. Now just find out the ratio of this. So we can say this is 4:3. 4:3. So that's why this ratio is 4:3. That's why formula becomes A4B3. Now try yourself. I have given the answers in some of the questions, but you have to find out how these answers came. Is it clear? Like calculate the number of atoms in a cubic based unit cell having 1 atom on each corner and 2 atoms on each body diagonal. You have to find out the number of atoms in a cubic based unit cell having 1 atom on each corner and 2 atoms on each body diagonal. Just find out the answer. If you are feeling the difficulty, contact to me. A compound formed by element X and Y has cubic unit cell in X. X atoms are at the corner of the cube. Just see what the contribution of corner, and Y atoms at the face center. Again see the contribution of face centers. What is the formula? What type of unit cells are possible for tetragonal crystals? This we have discussed in before video we have shared, that is unit cells, crystal lattice and unit cell. What type of unit cells in tetragonal crystal? You can see that one table which we already discussed. Name the crystal class for which all the 4 types of unit cells are possible. This again we already discussed. This is question number 5 and 6, which is, this is again based on the calculation whatever we have discussed today. So just verify the answers. If you have any difficulty, contact me. Thank you.